Picture this for a moment. Really, you're sitting somewhere right now, maybe on your couch, maybe at your desk. Your heart beats about once per second. Steady, predictable. Now imagine trying to grasp something that happened in less time than it takes for light to travel across a single proton. That's where our story begins. 13.8 billion years ago, everything changed. Or rather, everything began. In one moment, there was nothing. The next, everything. All the matter that makes up you, me, every star you've ever seen, every galaxy we've discovered. It all emerged from something smaller than the smallest thing you can imagine. And I mean that literally. We're talking about scales so tiny that calling them microscopic would be like calling the Pacific Ocean damp. This isn't just the biggest question in science. It's the question that makes physicists lose sleep, that crosses every boundary between what we can test and what we can only dream about. We understand so much about how things work: mechanism, process, cause, and effect. But when it comes to the ultimate cause, we hit a wall. Stephen Hawking once suggested maybe there really was nothing before. Think about that. Not empty space, because space itself didn't exist. Not a long stretch of time with nothing happening, because time hadn't started yet. He compared it to asking what's north of the North Pole. The question itself stops making sense. Actually, let me back up because this gets even stranger. The hottest thing ever. Where's the hottest place in the universe? You might think it's inside a star. The center of our sun reaches about 15 million degrees Celsius. Well, it's hot enough to fuse hydrogen into helium, which is saying something. But it's practically freezing compared to what we need to talk about. Supernovas? Sure, they hit 100 billion degrees when a star explodes. Still not even close. The hottest temperature ever recorded anywhere in our vast cosmos happened 100 meters beneath snow-covered ground in Switzerland. At CERN's Large Hadron Collider, scientists smashed two lead atoms together in 2012 and very briefly, created a temperature of 5.5 trillion degrees Celsius. But even that's nothing compared to the Planck temperature, 10 to the 32nd power Kelvin. That's a 1 with 32 zeros after it. At that temperature, the very concept of temperature starts to break down. Particles would be moving so fast, vibrating with so much energy, that they'd tear themselves apart. This was the temperature of the entire observable universe in its first moment. Everything that you can see tonight when you look up at the stars, everything detected by our most powerful telescopes, it all fit into a space 1 Planck length across. That's about 100 million trillion times smaller than a proton. I know, these numbers are impossible to really understand. Our brains evolved to deal with things like, will that lion eat me? And is this fruit ripe? Not what happens when you compress the entire observable universe into a space smaller than the smallest thing that can theoretically exist. The age of chaos. This first period, lasting about 10 to the negative 43 seconds, that the decimal point followed by 42 zeros, and then a 1, is called the Planck era. And it's weird. I mean, really weird. Today, everything we experience is governed by 4 fundamental forces. Gravity keeps you in your chair. The electromagnetic force lets you see these words. The strong force holds atomic nuclei together. Actually, wait, let me show you how these all work together in something as simple as watching TV. When you pick up the remote, you're overcoming gravity with your muscles. The remote sends invisible infrared light across the room. That's electromagnetic radiation. The picture lights up through millions of pixels emitting visible light, which travels to your eyes. Inside your brain, neurons fire up to 200 times per second to process what you're seeing. All of that depends on atoms staying together, courtesy of the strong nuclear force. Oh, and the potassium in your body that helps those neurons fire, It's slightly radioactive. About 5,000 potassium atoms decay every second in your body, driven by the weak nuclear force. But in the Planck era, these four forces might have been one single, unified force. Or maybe not. We honestly don't know because our two best theories about how the universe works completely break down. See, Einstein's general relativity describes gravity beautifully at large scales. Quantum mechanics perfectly explains the very small. But in the Planck era, we need both, and they're incompatible. It's like needing to be in two places at once. The math just doesn't work. John Wheeler, a physicist in the 1950s, gave us probably the best image we have, quantum foam. Imagine space-time itself bubbling and frothing randomly. Microscopic black holes and wormholes pop into existence and disappear without cause. The orderly universe we know, where causes have effects and time moves forward, none of that existed yet. The forces divide. After that first incomprehensible fraction of a second, things start to make slightly more sense. The universe expanded and cooled, though cooled is relative when we're still talking about 1,000 trillion degrees. Here's something cool. The forces we know started to separate like, imagine flipping a coin. While it's spinning in the air, you can't see heads or tails, it's just a whirling disk. Only when it lands and stops can you see which side is up. The fundamental forces were like that. At high enough energies, they blur together. As the universe cooled, they separated and became distinct. First, gravity broke away. Then, in the grand unification epoch, we had just two forces, gravity and something called the electrostrong force, a combination of what would become the electromagnetic weak and strong forces. The universe was still smaller than a quark. Particles were having complete identity crises. Quarks becoming leptons, matter becoming antimatter, everything transforming into everything else in a subatomic free-for-all. Then something happened that would determine absolutely everything about the universe we see today. The Big Bang's big problem. By July 2022, the James Webb Space Telescope had been operating for barely a month when it sent back images that made scientists question everything. Astronomer Alison Kirkpatrick wrote that she found herself lying awake at 3 a.m., wondering if everything she'd ever done was wrong. The telescope had spotted galaxies from when the universe was only 200 million years old. But these weren't the messy, chaotic proto-galaxies we expected. They were organized, structured, way too mature for their age. Some media outlets ran with this, claiming Webb had disproved the Big Bang. Nonsense. But it did highlight something crucial. There's a piece missing from our understanding. Actually, there were three big pieces missing even before Webb started sending back those images. First, the horizon problem. Look in any direction and measure the universe's average temperature. It's 2.7 Kelvin everywhere. All 93 billion light years of the observable universe. But how did opposite ends of the universe, which can't have been in contact because even light hasn't had time to travel between them, end up at exactly the same temperature? Second, the flatness problem. The geometry of space-time appears perfectly flat. Not curved like a sphere, not saddle-shaped, flat. The odds of this happening by chance are like flipping a coin and having it land perfectly on its edge. Third, and this is my favorite, where are all the magnetic monopoles? Every magnet we've ever found is both a north and south pole. You can have positive charges alone, negative charges alone, but never a north pole without a south. Theory says they should exist, but we've never found even one. The solution that changed everything. On a December night in 1979, physicist Alan Guth had an idea that would solve all three problems at once. Instead of the universe expanding gradually over billions of years, what if it had suddenly inflated exponentially in less than a trillionth of a second. Let me put this in perspective. Take a sheet of paper 1/10 of a millimeter thick. Fold it once. Now it's 2/10. Fold it 7 times. It's as thick as a notebook. 23 folds would make it a kilometer thick. 30 folds would reach space. 42 folds would get you to the moon. 90 folds, the number Goose proposed for cosmic inflation, would make that paper wider than the entire Virgo supercluster of galaxies. That's what happened to our universe in less than a picosecond. This sudden inflation explains everything. The universe appears uniform because our observable bubble is just one tiny patch of something much larger. It looks flat for the same reason the ocean looks flat from a beach. We can't see far enough to detect the curve. And magnetic monopoles? They're probably out there, but inflation spread them so far apart that there might only be one in our entire observable universe. Now here's where things get personal. I mean, literally personal. We're about to talk about where the matter that makes you came from. The universe gets mass. After inflation, the universe was vast, cold, and empty compared to a moment before. Well, cold, meaning only about 1,000,000,000,000 degrees. And this is when one of the most important events in cosmic history occurred. Particles got mass. Think about that for a second. Mass seems so fundamental, so basic to what matter is. But originally, particles were massless, zipping around at the speed of light. Then something changed. Peter Higgs figured this out in the 1960s while teaching in Edinburgh. He suggested that a new kind of field emerged and filled all of space-time, like an invisible molasses that some particles stick to more than others. The more they stick, the more mass they have. The British government actually offered a prize for the best analogy to explain this. David Miller won with a cocktail party metaphor. Imagine a room full of partygoers. A regular person walks through easily. But when someone famous enters, maybe a Nobel laureate, everyone clusters around them, slowing their progress. That clustering is like mass. It took 50 years to prove Higgs was right. Scientists had to search for the Higgs boson, the particle associated with this field, without even knowing what energy level to look at. Like searching for a needle in a haystack when you don't know what a needle looks like. Finally, in 2012, the Large Hadron Collider found it. Without the Higgs field, electrons wouldn't orbit nuclei. Atoms wouldn't form. Chemistry wouldn't exist. You wouldn't exist. The universe chooses sides. Here's something that should bother you. You shouldn't exist. Actually, nothing should exist. When a universe creates matter from energy, it always creates equal amounts of matter and antimatter. They're opposites. When they meet, they annihilate each other completely, converting back to pure energy. Think about what that means. Every proton should have had an antiproton partner. Every electron, a positron. They should have all found each other, annihilated, and left nothing but light. But here you are, made of matter, reading this on a device made of matter, on a planet made of matter. Something tipped the balance. For every billion antimatter particles, there were 1,000,000,001 matter particles. That tiny difference, 1 in 1,000,000,000, is why anything exists at all. We still don't know why. It might be related to neutrinos, those ghost particles that barely interact with anything. We've only ever found left-handed neutrinos and right-handed antineutrinos. Where are their opposites? Maybe they existed in the early universe, but decayed in a way that favored matter over antimatter. We just don't know. Actually, let me tell you about neutrinos because they're absolutely wild. The ghost particles. Right now, as you read this, about 100 trillion neutrinos are passing through your body every second. You don't feel them because they barely interact with matter at all. A neutrino could pass through a light year of lead and probably not hit anything. Scientists first predicted neutrinos in the 1930s when they noticed energy was missing from certain nuclear reactions. Wolfgang Pauli called them a desperate remedy to save conservation of energy. But how do you detect something that ignores almost everything? In the 1950s, two physicists named Cowan and Reynes had a crazy idea: detonate a nuclear bomb and put a massive detector 50 meters away. Even their colleagues thought that was too crazy. So instead, they used a nuclear reactor and finally detected neutrinos in 1956. Today, we have neutrino detectors in the strangest places. There's one called Ice Cube in Antarctica. It's a cubic kilometer of ice with over 4,000 sensors frozen deep inside. Scientists melted 80 holes, each 2.5 kilometers deep, with hot water. It took 58 hours per hole. And this massive detector, it catches maybe a few neutrinos per day. But here's the thing. Neutrinos were one of the first particles to break free in the early universe, around 1 second after the Big Bang. While light was still trapped for another 380,000 years, neutrinos were already streaming freely. If we could detect these primordial neutrinos, we'd see the universe as it was at 1 second old. The first black holes. Speaking of mysteries, let me tell you about TON 618. It's a black hole 66 billion times more massive than our sun. Actually, scratch that. It's heavier than all the stars in our galaxy combined. Its event horizon is 40 times wider than Neptune's orbit. Here's the problem. We see supermassive black holes that formed when the universe was less than 1 billion years old. But our models say there hasn't been enough time for enough stars to live, die, and create black holes that big. Stephen Hawking suggested a solution back in 1971: primordial black holes. What if some formed directly from the dense soup of the early universe? No stars required. In that first second after the Big Bang, when everything was still incredibly dense, gravity could have collapsed regions directly into black holes. These could range from microscopic ones weighing less than a paperclip to monsters 100,000 times heavier than the sun. We haven't definitively found any yet, but they could be the seeds that grew into the supermassive black holes we see today. The universe learns to fuse. On December 5th, 2022, humanity did something the universe figured out in its first minute: nuclear fusion that produces more energy than it consumes. At the National Ignition Facility, scientists focused 192 lasers on a pellet the size of a peppercorn. They heated it to 3 million degrees Celsius, compressed it to 100 billion times atmosphere pressure, and for less than 10 billionths of a second, turned hydrogen into helium. Energy in: 2.05 megajoules. Energy out: 3.15 megajoules. Enough extra to boil about 20 kettles. The universe did this naturally when it was about 10 seconds old. The temperature had dropped to only 10 billion degrees. Protons and neutrons started combining. First into deuterium, 1 proton, 1 neutron. Then helium-3, then helium-4. But there was a bottleneck. Deuterium kept getting destroyed by the intense radiation until the universe cooled enough, about 300 seconds in. Then, for about 20 minutes, the entire universe was a fusion reactor. When it was done, the universe was about 75% hydrogen and 25% helium by mass, with tiny traces of lithium and beryllium. That ratio, 75/25, is exactly what we still see today. Even after 13.8 billion years of stars fusing hydrogen into helium and heavier elements, the universe's overall composition barely changed. That's how much helium was made in those first 20 minutes. Think about that. The deuterium in Earth's oceans, the helium in party balloons, it didn't come from stars. It was forged in the first minutes after the Big Bang. The first chemistry. For the next 100,000 years, the universe was still too hot for atoms to form. Electrons were free, zipping around, making the entire universe opaque to light. Imagine the whole universe as a glowing fog. Light couldn't travel more than a tiny distance before hitting an electron and bouncing off in a random direction. But something was happening in that chaos. The first molecular bonds were forming, not molecules as we know them. These were weird, unstable things that could only exist in those extreme conditions. The first was helium hydride. Helium, the most antisocial element, the noble gas that wants nothing to do with other atoms, was forced to bond with hydrogen because hydrogen ions desperately needed electrons, and helium was the only atom cool enough to have captured any. It took until 2019 to detect helium hydride in space. Scientists had to use a telescope mounted in a modified Boeing 747, flying at 43,000 feet to get above most of Earth's water vapor. They found it in a nebula 3,000 light-years away, confirming what theorists had predicted for decades. Let there be light. Finally, 380,000 years after the Big Bang, the universe cooled to about 3,000 Kelvin. Electrons could finally join nuclei to form stable atoms. In that moment, the universe went from opaque to transparent. Light that had been trapped for hundreds of thousands of years could suddenly travel freely. This light is still around. We can see it. It's called the cosmic microwave background, and it's everywhere. The discovery was an accident. In the 1960s, two researchers at Bell Labs were trying to study radio signals from space, but they kept hearing this annoying hiss from every direction. They thought it might be pigeon droppings in their antenna. They actually called it white dielectric material in their notes. Scientists are so formal. They cleaned the antenna, relocated the pigeons. The hiss remained. Turns out they discovered the afterglow of the Big Bang itself. The light from when the universe became transparent, stretched by 13.8 billion years of expansion from visible light to microwaves. It's the oldest light in the universe, and it's hitting your body right now. This is where a story gets unsettling, because everything I've told you so far, it's only about 5% of the universe. The missing pieces. In 1933, Fritz Zwicky was studying a cluster of galaxies when he noticed something wrong. Actually, very wrong. The galaxies were moving way too fast. Based on the stars he could see, there wasn't nearly enough gravity to hold the cluster together. It should have flown apart billions of years ago. His solution? There must be matter we can't see. He called it Dunkel Materie, dark matter. Nobody took him seriously for almost 50 years. Then in the 1970s, Vera Rubin was studying how galaxies spin. She expected stars at the edges to move slower than those near the center, like planets in our solar system. Instead, stars at the edges were moving just as fast as those near the center. The only way this made sense was if galaxies were surrounded by huge halos of invisible matter. We now know dark matter outweighs normal matter 6 to 1. The Milky Way's dark matter halo extends maybe 15 times farther than the stars you see. Everything we see, every star, planet, every atom in your body, we're just the foam on an invisible ocean. We don't know what dark matter is. It could be machos, massive compact halo objects, black holes, neutron stars, failed stars too dim to see. Or it could be WIMPs, weakly interacting massive particles. Completely new particles that don't interact with light or normal matter except through gravity. Every experiment to detect dark matter directly has failed. We know it's there, we can see its gravitational effects everywhere, but we can't touch it, see it, or figure out what it is. And that's not even the weirdest part. The universe accelerates. In 1998, astronomers studying distant supernovas discovered something that shouldn't be possible. The expansion of the universe isn't slowing down as gravity should make it. It's speeding up. Something is pushing the universe apart, and that something makes up 68% of everything. We call it dark energy because we have no idea what else to call it. Think about what this means. Everything you see, all the stars, all the galaxies, all the normal matter, and even all the dark matter, adds up to just 32% of the universe. The rest is this mysterious force pushing everything apart. Einstein actually predicted something like this, called the cosmological constant. He thought empty space might have its own energy. As space expands, you get more space, therefore more energy, causing more expansion. But the numbers don't work out. Quantum mechanics says empty space should have energy from virtual particles popping in and out of existence. But the predicted amount is wrong by a factor of, well, it's been called the worst prediction in the history of physics. So maybe it's something else entirely. Some physicists propose quintessence, a field that can be attractive or repulsive and changes over time. But we have no evidence for it. We're literally in the dark about dark energy, how it all comes together. Let me paint you the full picture. A million years after the Big Bang, the universe entered what we call the Dark Ages. No stars yet, no light except the fading glow of the Big Bang itself. But dark matter was already at work. Remember those tiny variations in the CMB, those hot and cold spots? Dark matter felt those too. But while normal matter was still bouncing around, too hot to clump together, dark matter, which doesn't interact with light or radiation, started collapsing into the first structures. Dark matter formed a cosmic web, invisible filaments and nodes stretching across the universe. Normal matter followed, flowing into the gravitational wells dark matter had created. Without dark matter, galaxies wouldn't have formed when they did. Stars would have taken much longer to ignite. We might not be here at all. 10 million years passed. 100 million. Finally, in the densest clumps, hydrogen gas compressed enough to ignite the first stars. These weren't like stars today. They were monsters hundreds of times more massive than our sun, burning bright blue-white and dying after just a few million years in spectacular supernovas that seeded space with the first heavy elements. Galaxies formed and merged. 10 billion years ago, our Milky Way was in its prime, a beautiful spiral producing stars at a phenomenal rate. About 5 billion years ago, in an unremarkable arm of that galaxy, our sun formed from a cloud enriched with elements from countless dead stars. Earth formed. Life began. And somewhere in the last few million years, on the third rock from that average yellow star, something unprecedented happened. Matter became aware of itself. The universe developed the capacity to wonder about its own origins. The biggest questions. So here we are. We've traced the universe from the first incomprehensible fraction of a second to today. But the biggest questions remain unanswered. What came before? Was there a before? Are we one universe among infinite others, each with different constants, different laws of physics? Is that why our universe seems so fine-tuned for complexity, for life? Because all the universes that weren't suitable don't have anyone in them to ask these questions? We know the universe is 13.8 billion years old. We know it's expanding, and that expansion is accelerating. We know we're made of stardust, literally. Every element heavier than helium was forged in a star. We know we're only 5% of everything, swimming in an ocean of dark matter and dark energy we don't understand. But maybe that's the most human thing about this whole story. Here we are, tiny collections of atoms on a speck of dust orbiting an average star, and we've figured out how it all began. We've detected light from when the universe was 380,000 years old. We've recreated conditions from the first microsecond after the Big Bang. We've discovered we're mostly ignorant about 95% of everything. which is its own kind of knowledge. You know what strikes me most about this story? The universe started as pure chaos. Quantum foam, particles appearing and disappearing, forces unified in ways we can't imagine. And from that chaos came order. Forces separated, particles gained mass, atoms formed, stars ignited, galaxies spun into being. On at least one planet, chemistry became biology. Life evolved, diversified, and eventually produced minds capable of understanding where they came from. The universe evolved the capacity to know itself. And that might be the most amazing part of all. Not just that we exist, but that we can stand here 13.8 billion years after it all began and piece together this incredible story. We're the universe looking back at its own baby pictures, trying to understand how it grew up. The next time you look at the night sky, remember, you're not just looking at stars. You're looking at your cosmic family tree. Every atom in your body, except hydrogen, was forged in a star. You're looking at the 2.7 Kelvin microwave background that's been traveling since the universe became transparent. You're looking at dark matter's invisible architecture holding everything together. And somewhere out there, perhaps other collections of atoms have also become aware, also wondering how it all began. Because in a universe this vast, this old, this strange, anything seems possible. Even us.